Hello and good evening, everyone. So today we will be discussing some of the questions and assignment related to week 10 of the NMR course of the NPTEL course, NMR Spectroscopy for Chemists and Biologists. So I welcome you all to the week 10 problem solving session of this course. So I will wait for 5 minutes and then I will start today's session. So I hope all of you are able to follow what is being taught in the lectures and you have gone through the week 10 lectures. So today we will mainly deal with multidimensional NMR spectroscopy and specifically two-dimensional NMR spectroscopy and a little bit more detail I will talk about the COSY experiment. So we will understand the concepts and also we will solve the questions related to these concepts. So I will wait for another few minutes and then I'll start sharing the slides for today. Okay, so I will start today's session. Yeah. So I hope the slides are visible. And yeah, so hello everyone. I am Akash Jyoti Pathak. I am a PhD scholar in the Department of Biosciences and Bioengineering in IIT Bombay. And I am the PMRFTA for this NPTEL course, NMR Spectroscopy for Chemists and Biologists. So today we are in the week 10 problem solving session. So let's start with today's session. Okay. So starting with multidimensional NMR, what is the general scheme of a multidimensional NMR spectroscopy? So if we look at the general scheme, so there are three parts in this general scheme. One is the preparation time, then there is evolution time, and then detection. Okay. So the generalized scheme of multidimensional NMR experiment is segmentation of the time axis. So here you see that the time is segmented T1, T2, Tn, and following this evolution, this is also called the evolution period. And after that, following that, the detection is taking place. Okay, so what is the preparation period? So in the preparation period, the XY magnetization is created. So so here a pair of 90-degree pulses is separated by a constant evolution time constitutes the preparation period. So the 90-degree pulses are separated by constant evolution time. So these are the T1, T2, followed by and up to Tn. These are the evolution periods. And so the evolution periods T1, T2, T up to Tn are variable and generate n plus one dimensional time domain data, which after n plus one dimensional Fourier transformation is the n plus one dimensional spectrum. Right. Okay. So you are you collect the data in the time domain and then you Fourier transform it to get the data in the frequency domain. Okay, so there are various types of manipulations within the frequencies are possible during these periods. So in the evolution period, so in this T1, T2 up to Tn, what does this in evolution period? What it is allowing is it is allowing to manipulate allowing the manipulations of the frequencies during these periods. And this M1, M2, Mn, these are called the mixing periods. The mixing period establishes correlations between frequencies in adjacent evolution period. So what is the correlation between the frequencies in this adjacent evolution period? So after an evolution period T1 is applied, then a mixing period is applied. And in this mixing period, what is happening? The mixing period helps establish correlation between frequencies in adjacent evolution periods. Now, different kinds of correlations can be established by exploiting different types of interactions between the spins. Okay. So, yeah, different kinds of correlations can be established by exploiting different types of interactions between the spins. The most common type of interactions exploited are the J-coupled interactions and through space dipolar interactions. Okay. So here you understood what is the general scheme of a multidimensional NMR. So there is a preparation time, then this is followed by evolution periods, and then the mixing periods, and following these mixing periods, then you detect then you convert basically what you do is convert the time domain into frequency domain, and then you get the peaks of the NMR signals. Okay. Now, what in so this is a So now coming to specifically to two-dimensional NMR. So the first figure here, it shows the general scheme. So there is a preparatory time, then evolution, then mixing period, and then detection. Okay. Now what happens in the evolution period? In the evolution period, you increment it in T1 plus there is increments of T1 time. Okay. So the first figure, this what it explains is this is the segmentation of time axis. Okay, this is the segmentation of time axis for the for two-dimensional experiment. Okay. So for a two-dimensional experiment, how how the segmentation of time period is done. It is shown here by a schematic diagram. And what does this figure B indicate is the so these this indicates the details of the experiment, uh, showing the systematic increments of the evolution period T1. Okay, so systematic increments for time period T1. Okay, so what it is basically happening is in this preparation time, the XY magnetization, yeah, you are giving different pulses at 90-degree pulses, and then T1, then mixing period, then T2, then 2T1, and again M2, then another T1. So that is here what it is shown over here. Okay, so del T1, then mixing period, and then you detect the signal, and then 2 del T1 mixing period, and then you detect. So it is a so there is increments for the time period T1. So what are the P and M? What does it indicate over here? So P is indicating the preparation period. Okay, P is the preparation period, and M is what? M is the mixing period. So P is the preparation period and M is the mixing period, and T1 or T2 are the evolution and the detection periods respectively. Okay. So T1 is the evolution period and T2 is the this is the evolution period and T2 is the detection period. Okay. So basically what is happening? So the experiment involves a collection of a number of free induction decays for systematically incremented values of T1. Okay, so these are the free induction decay. We had discussed what is free induction decay in detail. So with increments of T1, you are detecting the free induction decay. Okay, so to summarize the what is it the what is doing it the experiment. It involves collection of a number of free induction decays for systematically incremented values of T1. Okay, so the experiment is this schematic figure in B. What it shows is that it shows the experiment which is involving collection of a number of free induction decays systematically with incremented values of T1. So del T1, del 2, del T2, and 3 del T1, and so on. And the final data set, what will you get there for in the final data set? The final data set, you will get a matrix, right? You will get a matrix having T1 values and T2 values. So it will be a T1. You will get a matrix with T1 and T2 values and Fourier transform. You will once you do the Fourier transform with respect to T2, it will result in one-dimensional spectra in which the amplitude and phases of the signal depend upon the values of T1. So variation of these entities as a function of time carry the frequency information present during the T1 period. And the Fourier transform of these data along the T1 results in a two-dimensional frequency domain spectra as F1, F2. Okay. So you are doing Fourier transform. So with increments of T1, you are detecting the successive increments of T1. You are detecting the Fourier. You are detecting the free induction decay, and so in the free induction decay, you get it in the T1. You have the T1 and T2 values, and then you Fourier transform it to get the frequency information. Okay. So yeah, so summarizing this, what it is doing. So what all I said is Q is the preparation period, M is the mixing period, and T1 and T2 are the evolution period and the detection period. And the experiment will involve a collection of a number of it will involve a collection of a number of free induction decays for systematically incremented values of T1. And so what you will get is you will get a matrix with the T1 and T2 values and the Fourier transform. Fourier transform with respect to T2 will result in a series of one-dimensional spectra in which the amplitude and so you Fourier transform it and then you get the amplitude and phase information, right? Uh, with the amplitude with respect to in which the amplitude and phases of the signals depend upon the values of T1. So variation of these entities as a so what is the variation of these intensities as a function of time that will carry the frequency information present during the T1 period. Okay, and this okay. So yeah, so that is what I was trying to explain through the figure. So here you can see it has been explained in detail. So the experiment involves a collection of number of free induction decays for systematically incremented values of T1. And the final data set will thus be a matrix S, the matrix uh, on S, it will have two values, T1 and T2. Okay. Now, Fourier transformation with respect to T2 will result in a series of one-dimensional spectra in which the amplitudes and phases of the signals depend upon the values of T1. Okay. So variation of these intensities as a function of time carries the frequency information present during the T1 period. So during the evolution period, what is the frequency information that with increments of time that you can get, right? And the Fourier transformation of these data along the T1 results in a two-dimensional frequency domain spectrum as F1 to F2. This is what I was explaining. Just a second, I will erase this. Okay. F2. So T1, what does T1 indicate? It indicates the indirect time evolution. Okay, not directly detected but varied across experiments. So what are we doing? That is T1 time. This is varied across experiment depending upon what type of experiment you want to perform. There are different types of NMR spectroscopy experiments, 2D NMR experiments. So depending on what type of you can vary this T1. So we are not detecting anything during this T1 time. That is why it is called the indirect time evolution. Okay. So in this T1 time period, you are allowing you are giving different pulse sequences and this XY magnetization will take place, and then in the T2 time period, what is that is the detection period, right? T2 is the detection period, so that is the direct time during which the data is collected, leading to a spectrum after Fourier transformation. So that so T2 we will this detection time, that is that Fourier transform, and then we will get the signal. Okay. Yeah. So So the evolution period T1, T2, Tn are variable and generate n plus one dimensional time domain, which after n plus one dimensional Fourier transformation is the n plus one dimensional spectrum. Okay. Okay. Now, what does this figure indicate? So, this is again a schematic of the processing of the two-dimensional data, ST1, T2. Okay. So, basically, what you're doing this one too. Is F1, F2 by Fourier transformation, right? So what are the steps that is taking place that is shown in this schematic? So it is the processing of the two-dimensional data as T1, T2. So these are the individual FIDs, right? At zero time, at delta T1 time, 2 delta T1. These are the individual FIDs. The first, so this is the first column, and this first column indicate the individual FIDs. So collected for T1 time points, and they are then Fourier transform. So this is the FID at different time points, and then Fourier transformation of this will give you this frequency. The will give a single line in this the frequent and the frequency domain, and then so this is the column one basically. So in column one, these are the free induction decay, then these are Fourier transform, and then you get this single peak. And then by taking the intensities, now you take the intensities at each point. You take the intensities at each point on the discrete F2 spectra. So this is the F2 spectra, okay? So then this F2 spectra, you take the individual each point, and then we arrive at the, what we will get? We will arrive at the T1 dependent profiles. These are the T1 dependent profiles in this column 3. So these are the T1 dependent profiles, and these FIDs are then Fourier transform to generate the, these are again Fourier transform to generate the spectra along the F1 axis. For illustrate, so what is happening? So in F1 and F2 spectra, we see the intensity modulation as we move through this frequency axis. So these are the free induction decays. So these free induction decays are first Fourier transform, and we get the spectra F in the F2 dimension. In the F2 dimension, then these each points, then taking the intensities at each point, we again Fourier transform it to get the frequency in the F2 dimension. Okay, this is collected at different time points T1 and then this F1, this is F2 is T1 dependent. So these are the F1. F1 is, this is the T1 dependent time profile. And this is the T2 dependent time profiles. Okay. Second, I will erase this one. T2 dependent time profile. Okay. Now, answers after understanding this, try to answer this question. In a 2D NMR experiments, which of the following statement is correct? Data is explicitly corrected during the two independent time variables T1 and T2. Data is explicitly collected only during T2. Data is explicitly collected only during T1. And the last option is the spectrum is generated by frequency selective excitations along the two frequency axes, F1 and F2. So what will be the answer to this question? You have to pick the statement which is correct in these four options. So we just now we understood the general scheme. We have this preparation time, then evolution time, then after the evolution period, we have the mixing period, and then you have the detection period, right? So this evolution period was called as T1 and this one was called as T2. So now, given this hint, try to solve this question. Which of the following statement is correct? Data is collected during which period? Yeah. So yes, you have guessed it correctly. The answered it correctly. The answer is option number B. So in a typical 2D NMR experiments, there are two time variables that are involved. One is the T1 and another is the T2. So the evolution of the spin system during T1. So in the T1 time period, what is allowed? The evolution of the spin system is allowed, and this leads to encoding of the frequency information along the indirect dimension F1. Right. So just now we saw that there is this reinduction decay, and this reinduction decay is converted into this Fourier transform, and we get this F2, right? And then the intensities at each point, intensities of at each point, they are again Fourier transformed, and we get the F1 we get the frequencies in the F1 dimension, right? So the evolution of the spin system during T1 leads to encoding of the frequency information along the indirect dimension, but data is not explicitly collected during this period. So in this period, the data is not collected. Instead, T1 is incremented systematically, and the experiment is repeated for each increment, ultimately encoding this time dependence in the recorded data. So T1, 2 delta T1, 3 del T1. So with each increments of this T1 time period, the you are recording the FIDs. Okay, recording the pre-induction decay, but the data is not explicitly collected during this period. The actual data collection occurs during T2, which is the direct detection period corresponding to the F2 frequency axis. This means that the data is explicitly collected only during T2, right? And the T1 evolution information is encoded into the signal by varying T1 between acquisitions. Between each acquisition, we are increasing the time T1, and then the data is collected in the T2 time period. Okay. Now this question, try to attempt this question. The Fourier transformation of a complex NMR signal ST1, T2 leads to absorptive line shapes along both frequency axes, dispersive line shape along both frequency axes, absorptive line shape along F1, and dispersive line shape along F2. And the fourth option is mixed line shape along both frequency axes. So we had discussed this absorptive line shape and dispersive line shape in week 4 we had discussed. Week 4 or week 5 we had discussed in detail about the free induction decay and how we convert this time domain into frequency domain, and on conversion what is the absorptive line shape, what is the dispersive line shape. So if you remember the lecture, uh, this question is based on that concept also, and also on this concept. So you can also refer to this figure, right? So you can take the help of this figure. You see here. You Fourier transform it, and then you get different these line shapes, right? Here also you get different dimensions. Now try to answer this question. So I'll give you 2 minutes to think upon this. So in the F1 absorptive line shape, I hope you remember you get this type of spectra is called an absorptive line shape. And when you get spectra in this is called a dispersive line shape. This is called a dispersive line shape. Okay. So Fourier transform of the time domain into frequency domain can yield to a different line shape, dispersive line shape, and this absorptive line shape. So absorptive line shape is bell shaped, and here you will get above positive, above the zero axis, you get a spectra, and there is a negative peak also here. So as you were seeing, the correct answer for this question is option D. So in 2D NMR, so I was showing you this figure because you see here you Fourier transform it and then you get both this peak and this peak also. Okay. Similarly, here also you can get both the peaks, the absorptive and the dispersive line shape. Okay. So in 2D NMR, after performing Fourier transformations along both the time variables T1 and T2, the resulting spectrum can have a mixed phase. So this means what is a mixed phase means? So in mixed phase, it will mean that it will have both the absorptive and the dispersive components, and they are present along both the frequency axis F1 and F2. And the combination of this real and imaginary components corresponding to the absorptive and dispersive signals, they often leads to mixed line shapes, which can appear in both dimensions of the spectrum. So even in the F1 dimension and in the F2 dimension, so in a 2D NMR, you have this F1 dimension and F2 dimension. In the F1 dimension, you will have you can have both this absorptive line shape and dispersive line shape, and similarly in the F2 also you can have both the absorptive and the dispersive line shape. And the resulting peaks might show different peaks depending on the method of detection and processing. This occurs due to the interplay between the real and imaginary parts of the transform data. So all these concepts I have already discussed in this week 4 or week 5 problem solving session. Okay, now coming to this time proportional phase increment. So this time proportional phase increment, it is a method used for quadrature detection in the indirect dimension of 2D NMR experiments. So in the indirect dimension of 2D NMR experiment, what does this mean? It means in the T1 time period or in the evolution time period. So in the quadrature detection or quadrature FTNMR sessions, we had discussed about this quadrature detection in which the carrier and receiver, they are placed orthogonal to each other. And so in the quadrature detection, both the sine and cosine components of the signal need to be recorded to resolve phase information and avoid artifacts such as folding. So signal folding, also we had seen this. So what does TPPI do? It involves systematically incrementing the phase of the RF pulse by 90 degrees for every successive T1 increment. So with every successive T1 increment, you are increasing the phase by 90 degrees. And this method helps distinguish positive and negative frequencies in the F1 dimension and ensures that the phase information is retained correctly. Okay. Now, now this concept we had discussed about this dwell time and spectral width, right? So spectral width, what is spectral width? So the range of frequency for which the spectral width is the range of frequency for which the data is collected. So this is the spectral width, right? This one. This is called the spectral width. So what is the range of frequency for which the data is collected? That is called the spectral width. And what is the dwell time? So dwell time is the time between the time period, that is time period between two recording two successive frequencies. So between two successive frequencies, what is the time period? That is called the dwell time, right? And we are also looking to acquisition time. So acquisition time is what? It will be the dwell time into the number of data points that are there, right? So that will give you the acquisition time. So this dwell time and spectral width is inversely related because the more the spectral width, the the time between the two data points must be lower for getting high resolution spectra. So this is so why is it inversely related? So this is because the spectral width determines the range of frequency sampled, right? Range of frequency sampled, and to cover that range, the time between each sample data point. So between each data point, what is the time? That is called the dwell time, and that must be sufficiently small, right? So time proportional phase increment. So as the name suggests, so with each T1 increments, you are also you are also increasing the phase, the 90-degree phase. The RF, you are incrementing the phase of the RF bus by 90-degree, right? And then what is this? What this signifies, or how is this helping? So this method, this will help in distinguishing the positive and negative frequency. So what we were seeing that on when we were Fourier transforming that the T1 period, we were getting both the positive peaks and the negative peaks. Now, how will you distinguish between them? So for this method is applied, right? And this will ensure that the phase information is retained correctly. Now, based on this, so the TPP in TPPI, the phase is incremented by 90-degree for each T1 increment. However, this phase incrementation does not change the basic relationship between the dwell time and the spectral width. Okay, so in TPPI, this in this method, the phase is incremented by 90-degree by 90 degrees. So the RF pulse is changed by 90-degree for every T1 increment. But however, this will not change the spectral width. So the spectral width will anyway be inversely proportional to the dwell time. Or dwell time will always be equal to two times the spectral width. The dwell time in TPP still determines the spectral width along the T1 dimension. The TPPI method primarily affects how the data is processed to separate the real and imaginary components, but the time between increment remains dictated by the spectral width. To try to solve this question, just now I already gave you the answer, but try to solve it if say, spectral width is if SW is the spectral width along the F1 dimension of the 2D spectrum, and the carrier is placed at the center of the spectrum, right? So the carrier is always placed at the center of the spectrum in quadrature detection system, right? So then in the TPPI method of quadrature detection, the dwell time along T1 dimension will be equal to what? Yes, so just now we discussed this. So the dwell time, delta T, that is always equal to 1 by 2 times the spectral width. Right. It also looked into the Nyquist criteria based on this concept. A sort of question also related to this. The lesson is this dwell time will help us in getting more a better result spectra. Okay. So yeah, in the TPPI, the time proportional phase incrementation method. Time proportional phase incrementation method for quadrature detection. The dwell time along the T1 dimension is related to the spectral width. We saw this just now. The relation is given by this. Dwell time is equal to 1 by 2 times spectral width, where uh, also a spectral width along the F1 dimension. And this method ensures that both the negative and positive frequencies can be distinguished by manipulating the receiver phase during the T1 evolution period. I hope all these questions are clear. Now try to solve this question. Given the pulse sequence for the molecule CH3, CH2, CH2, Cl, the F2 axis of the 2D spectrum will show. So here a figure is given in this question. So this is the method of the pulse sequence that is followed for measuring the C13 spectra. You give it a 90-degree pulse in the X direction, then you allow a T1 time period, and then you detect the signal at T2. And then this H1 is decoupled. Okay, so you have to answer based on this one, this part. So what will you get? So CH3, CH2Cl. So how we decide the number of peaks we will get? The proton is decoupled over here in this pulse sequence, you see. So there is a decoupler, which means that this proton is decoupled, and then you have to determine the peak that you will get in the two axis. Okay. So we had studied the n+1 rule and when to apply them. So we see that there are three different protons in this case. There is a methyl proton, then there is a methylene proton, and there is another methylene proton, but this is coupled to the chloride atom, the chlorine atom. So all these three protons are in different chemical environment. They are in different chemical environments, so they will have different peaks. They will have their own magnetization, and when an external magnetic field is applied, they will show peaks at different positions, different frequencies in the NMR spectra, right? So because of this, this one will give up. This one will give us what? This one will give a triplet. This one gives us a because of this there will be a quartet, and because of this also we had seen this peak splitting. We had seen then CH2 will there will be a triplet for CH2 cell also. But here you have to apply the concept of doublet, triplet of triplet. Those concepts you have to apply here. But but you have to understand that here the protons are decoupled. So the correct answer will be what for this question? The correct answer will be you will get only three singlets, right? So option E is the correct answer for this question. So why is it so? So in this molecule, the 2D NMR pulse sequences can lead to singlets in the F2 axis if decoupling is applied during detection. So during detection, you are applying decoupling, right? You are applying decoupling. So that is why you will not observe the peak splitting. Okay. So if the proton decoupling is used, each proton environment will give rise to a singlet as all coupling neighboring proton is effectively removed. So since the protons are decoupled, so these ones, the CH3, CH2, these are decoupled. So these neighboring protons, the effect of these neighboring protons are removed, and so all these carbon are in these protons are in different environments. So you will get three singlets only. In order to as all coupling is effectively removed in the molecule, there are three distinct types of proton group. CH3, this methyl group, methylene group, and another methylene group which is bonded to the chlorine atom, and each of these will give a singlet in the F2 dimension when decoupling is applied. Thus, with decoupling, the spectrum will show three singlets along the F2 axis corresponding to three proton environments. Okay. I hope this is clear. You absorb this knowledge. So you have to look at the pulse sequence. You have to look carefully what is the figure that is given. So if a decoupling is applied during the detection time, then it means that the effect of these protons are removed. And so these three protons are in three different environments. So we are only will be getting three peaks for three singlet peaks for each of these three different protons. Right. Because the coupling to neighboring protons is effectively removed. Now we will learn about this J-resolve spectroscopy. So J-resolve spectroscopy, what does it mean? That a specialized type of 2D NMR experiment. It is a specialized type of 2D NMR experiment that is designed to separate chemical shift information from J coupling constants. So in 2D NMR experiment, you are measuring both chemical shift and also the J coupling. Okay. So for example, the frequency of C13 on one axis and proton on the other axis. So dimensions you are measuring simultaneously, right? So so if we want to separate this chemical shift information from this J coupling or the scalar coupling. So scalar coupling, we have known that this carbon is bonded to proton also. So depending on it, so depending on this carbon is coupled to proton, and the chemical shifts are related to the local magnetic environment of the nucleus, reflecting its electronic structure. So yeah, so what is the chemical shift? So the chemical shift will depend on the what is the local magnetic environment of the nucleus. Right. See, so whether this carbon is bonded to an alkene or whether it is bonded to some other electronegative atom. So depending on all these, the magnetic, it will have a local magnetic environment of its own. And that is what is given by this chemical. So from the chemical shift of these nuclei, we get this information. So if it is, so we had learned what are the various factors which will determine what will be the chemical shift of a particular nuclei, right? So the chemical shift will give us the information of what is the local magnetic environment of the nucleus. And then J coupling constant, it reflects the scalar interactions between spins, typically between nuclei connected by bonds. And they are responsible for splitting of the NMR signals into multiplets. So like we were seeing just now, the example of this CH3, CH2, CH2Cl. So what are the interactions between these different spins? The carbon will have a spin, and this proton also has a spin. How is it coupled, or how is it bonded to the other? nuclei to the other nuclei, and these will control this. These all will determine the splitting of this proton, right, of the neighbor. So the neighboring atom, what is the neighboring atom, and how is it coupled to the neighboring atom? How many protons are there in the neighboring atom? That will determine the splitting of that particular nuclei. So in J result spectroscopy, there are we get two types of information. So we have been discussing this. One is the F2. F2 is the T2 direct axis, and T1. So F2 is equal to T2, and the two types of information. One is the F2 axis, and another is the F1 axis, right? So this is the F2 axis, and this is the F1 axis. F1 axis. So F2 axis contains the chemical shift information, and this F1 axis contains the J coupling constants. Right, J coupling constant, and this separation helps resolve crowded spectra when overlapping multiplets in 1D NMR, where overlapping multiplets in 1D NMR obscure important information. Right. So in 1D, what is the necessity of 2D NMR? So in 1D NMR, you can use 1D NMR for small molecules, or for simple organic compounds. 1D NMR will give you peaks. Will give you peaks, and you can analyze that the peaks are corresponding to which nuclei. But for when the molecule is very large, for example, there is a protein molecule, you will have so many peaks, and it will become very difficult to understand that which peak is corresponding to which group. Because so, for example, if you consider that there is a CH3CH2 group, and there is some other groups, right? There is some other groups in between this, and then there is again a CH3CH2 group, in the end, or CH2CH3 group in the end. Then how? Then if you just do a 1D NMR experiment, then how will you analyze that this spectra? Is it because of this CH3CH2, or is it because of this one? So there will be multiple number of groups, right? There can be many CH3, CH2 groups in the entire protein structure, right? So if you so that it becomes so the a 1D NMR will give you many peaks, and the peaks corresponding, what are the peaks corresponding to the which group, that becomes difficult. So we need a 2D NMR experiment, or so in the 2D NMR experiment, there are two information, like we have the chemical shift information, and we have the J coupling constant. And based on this, we can now understand that what is which. If we have both this information, that what is the chemical shift and what is the J coupling, both this information will help us accurately determine that which group or which amino acid is corresponding to which peak, right? So, so for example, you can consider you all have a name. So there is a surname, and there is a name. You have a surname, and then there is the main name. So there can be many individuals having the same surname. But once you have the main name, then based on that, there will be, you can particularly identify, well, who is that person. So you need both the information. So that is why this two-dimensional NMR is required. So that is what is explained, is said over here, that this separation helps resolve crowded Prec spectra where overlapping multiplets in 1D NMRs obscure important information. So this CH3, CH2, this will have the same in 1D NMR spectra. You will have all the CH3, CH2 will give you the same, the peak at the same location, right? So that there will be a there will be crowding of spectra. So we need to separate this chemical shift information and the J coupling constant. Okay, so what is the pulse scheme for this J resolve spectra? So here it is shown here the pulse scheme for obtaining the separation of interaction in a homonuclear system. So in a homonuclear system means both the axes have one each, or C13 C13. So that is homonuclear system. And then in a heteronuclear system, there is, on one axis, you will have the information of proton, and on another axis, there is C13. So this is often referred to as the J resolved experiment. Okay. So this is the pulse sequence that is shown here. So you apply a 90-degree pulse in the x direction. Then there is a evolution time period for T1/2, and then there is a 180-degree pulse in the x direction. Then again there is T1/2 the evolution for T1/2 time period, and then you detect the signal in the T2 period. Okay. So so let me add one more slide. So if you have a what is the G? I'll just discuss this in a little bit more detail. G result spectroscopy experiment. So in this G result experiment, so if it is a weakly coupled two spin system, okay, weakly coupled two spin system, one spin is K and another spin is L, okay, and both are having I equal to half, and these are weakly coupled. So K and L are this is a weakly coupled spin system. Weakly coupled two spin system. So if we want to write the density operator for this weakly coupled two spin system, then what will you get? We have discussed about these density operators. So so if you want to write the density operator at different time points, okay. So along the pulse sequence, if we apply the density operator at different time points, then what we can write this rho one. So density rho one is the density operator, right? We represent the density operator as rho one. So at different time points, we can write this as I K Z plus I L Z, right? And then rho two, what we can write? Minus of I K Y plus I L Y. So what will happen during the next spin ecosystem, this one, during this next T1/2 time, during the next spin echo chemical, what will happen during the next spin echo period, chemical shifts will be refocused, and thus the spins evolved under the scalar coupling Hamiltonian Hj only. So explicitly, the evolution of the explicitly the evolution of the product operators are here it is shown for K only. Okay. Similar calculations apply for the spin L as well. Now rho to evolve under scalar coupling during the spin echo T1 and during the detection period T2. Thus, the total time period will be T1 plus T2. Right. So what you can next write is this. So these are the density operators at different time points along the pulse sequence. Along the pulse sequence, the rho 1 and rho 2 are the different. At different numbers, what is the density operator? Right. Now you can write it. If you solve this, what you will get is minus IK by Hamiltonian of this will give you what? Minus I K Y cos pi J K L T1 plus T2, right? And then you will get what? 2 I K X I L Z get sine pi JKT and then T1 plus T2. So during the next spin echo period. So during this T1/2 period, the chemical shifts will be refocused, right? And then it will be refocused, and then the spins evolve under this so scalar coupling constant Hamiltonian Hj only. And so the evolution of these product operators. So these product operators and these are shown for K only. And similarly, you can write for L. Okay. Now, so if you look at this equation, this equation. In this equation, the the second term, this one represents the antiphase magnetization. The second term, this one. So what does it represent? It represents antiphase magnetization is not observable during T2 period. So during the T2 period, you do not observe the antiphase magnetization. So considering the chemical shift evolution of the first term during the T2 one gets, so we will consider the chemical shift evolution of the first term. So we will this is the first term. So we will consider the chemical shift evolution of the first term during the T2. What we will get then? We can write this in this form. That is minus cos phi jkl T1 plus T2 IKY and then Hamiltonian Hj operator, we will get what? Minus cos pi jkl T1 plus T2 and then we will get this term. This one IKY cos omega k T2 minus IKX, right? And then we will get sine omega k T. Okay. So we will get this term. If we consider the chemical shift, the first term of the first term. And so if we assume that the Y detection, then the signal will be proportional to what? We are assuming only the Y detection. So it will be cos pi minus cos pi j kl T1 plus T2 cos. We will get only this one. So if we are assuming Y detection only. If we consider Y detection only, then what we will get? This one minus cos pi j kl T1 plus T2 cos omega k T2. This one only, this will get cancelled. This one will get cancelled, right? And then further subsequently what we can write is in this form minus give me a second. Okay, so now we can so the signal detection will be proportional to this one cos pi j, the coupling constant between this k and the k spin and the l spin, and the time period T1 plus T2. Then this. And now further we can write it in this form cos pi jkl T1 cos pi jkl T2 minus sin pi jkl T1 sin pi jkl T. So basically we are just what we are doing, we are expanding this one only. Okay. So finally we get this cos omega k T2. Okay. Two more slides. Yeah. So what did we get here? We got here minus cos pi j k l T1 cos pi j k l T2 minus sin pi. Yeah, what was this? Yeah. So there was sin, then again there was jkl T1 sin pi jkl T1. Okay. Cos omega k T2. Right? So what now what do we see here? If we observe this equation closely, we see that along the T2 axis, both chemical shifts and coupling constant. Right. So in the T2 axis, for what we see, if we observe this equation, we can see that in the T2 axis, there are both chemical shifts and J coupling in the T2 axis. But along the T1 axis, what do you find? The T1 axis, we only get the chemical shift. We do not get the chemical shift, we only get the scalar coupling information. We'll explain this through a figure that is on the next slide. So, yeah, this is what I was explaining. So in the F2 axis, you see this in the T2 we get both chemical shift and scalar coupling. Okay, but on the T1 axis, in the T1 axis, there is only information of the scalar coupling. Right, here is only information of the scalar coupling. And then what will happen? The peaks will align themselves at an angle of 45 degree. The peaks will align themselves at an angle of 45 degree with respect to this one, with respect to the F2 axis, and the detected signal has both cosine and in the detected signal there will be both cosine and sine components and sine modulations along both this T1 and T2 axis. The cosine modulations results in an absorptive shape. Said that there will be cosine modulations. So we were solving this question, right? So in the cosine modulations will give you this absorptive line shape. I'd like to just look at this figure and the absorptive line shape, this cosine we will get in both this T1 and T2 axis. Right. Cosine modulations will give you absorptive line shape in both this T1 and T2 axis, and the sine modulations will give you dispersed sine modulations. What do they give you? They give you dispersive line shape. It will give you the sine modulation will give you dispersive line shape along the T1 and T2 axis. So, so that is why what we were seeing that in this when I discussed this one of the questions before, in the F1 axis and F2 axis both have these mixed phases or mixed line shapes are present. And dispersive and the or the mixed phases will be present. Dispersive and the absorptive line shape because both this cosine you saw the relation just now there is both this cosine function and sine function and so both this f1 and f2 will have the this absorptive line shape and the dispersive line shape but but what we want to do, and what will this happen? Then this will require a magnitude mode calculation of the spectra, and such calculation can be extended to this one. So these calculations can be extended to a multi-spin system. So an experiment. This is an experiment. This demonstrate this multi-spin system and how this can be done. So what do we see in this figure? Basically, we see that the coupling information is present along both the axes, right? This coupling information. So in this experiment, the coupling information. So you see in the along the F2 axis also there is coupling information, and along the F1 axis also there is coupling information, right? Uh, and but what is desired? It is desired that this scalar coupling and the chemical shift are separated. They are dissolved. That is why they are called J dissolved spectroscopy. We want that the chemical shift is on one axis and the one is on the other axis. And this is performed by this one, the shearing transformation on the peaks. So since this coupling information is present on both the axis F1 and F2, and we desire that this information be present only on one axis. So chemical shift must be present on only this F2, and the scalar coupling should only be present in F1. So we perform this shearing transformation on peaks, and this is shown in this diagram. Okay, so after shearing, what do we get? So after shearing, what you can see, this F2 axis has only this chemical shift, and the F1 axis has only the scalar coupling. Okay, so that is what is known as the J dissolved spectroscopy. Okay. So in the J results, after all these the derivation and all the figures I showed, this what it, so in this J result spectroscopy, the F2 axis contains only the chemical shift information after the shearing transformation or shearing of the NMR peaks, right? We will get the direct axis will contain only the chemical shift information, and the F1 axis will contain the J coupling constant. And this helps in resolving the overlap that we were seeing in that we usually observe in 1D NMR experiment. Okay. So is this point clear to everyone? And this derivation, these expressions. So these are explained for this weakly coupled two-spin system. Okay. Weakly coupled two-spin linear system, right? Weakly coupled two-spin system, both are having I equal to half, and the two spins are K and L. And then we wrote the density operator terms at different time points. So at different time points, what will be the density operator along the pulse sequence? So along the pulse sequence, one is right along this x-axis. So along this pulse sequence, this rho one, you can write it as IKZ plus ILZ, right? And the rho two density operator. So this one rho 2, then you can write it as minus IKY plus ILY, right? And then if you so then in this pulse sequence, if you see that the spin echo periods, the what will happen, the chemical shifts will become refocused, and then the spins will evolve under the scalar coupling of the under the scalar coupling HJ only. Okay. So once this spin echo period is allowed, the The spins will evolve under the scalar coupling Hj, and the evolutions explicitly the evolutions of the product operators are shown for this k spin only. And similarly, you can also show this for the spin L as well. Right. And now row two. Row two is evolving only under the scalar coupling during the speed growth the time T1 and the detection time period T2. Thus, the total time period will be what T1 plus T2. So since the total time is T1 and T2, so we can write all these expressions, these minus IKY, and Hamiltonian is acting on this. And this one, the second term, it only gives us the, it is not observable. So this is not observable. So we proceeded with this first term. And in the first term, the chemical shift of this first term will give us this result. And finally, this is the expression. So we see that this T2 axis, the T2 axis has both the chemical shift and J coupling. Okay, so we do this J result. So now try to solve this question. In a homonuclear 2D J result spectrum, F1 axis has chemical shifts and F2 axis has coupling constant. F1 axis has coupling constant, F2 axis has chemical shifts and coupling constants. F1 axis has coupling constant, F2 axis has chemical shift. F1 axis has chemical shift and coupling constant, and F2 axis has chemical shift. So yeah, you see what does this? You see this figure F1 axis. What does this F1 axis have? Scalar coupling, and what does the F2 axis has? The F2 axis has chemical shift. Now, given this hint, try to solve this question. So it is a homonuclear 2D J result spectrum. So in the 2D J result spectrum, we are separating the chemical shift information and the scalar coupling information. Right. So here the options, these F1 axis, F2 axis, they have been jumbled. So we have to identify the correct option. I'll give you 2 minutes. Try to answer this question. So yeah, you do the shear transformation on this piece. Okay. Otherwise, in the F2 axis, there is both chemical shift and scalar coupling information. Now, when you perform the shearing transformation on the peaks, you get the chemical shift information on the F2 axis. Okay. Yeah. So the correct answer is option C. Correct answer is option C. That is the F1 axis has coupling constants and F2 axis has chemical shifts. Right. Just now we saw after we apply the shear transformation on. So the shear transformation of the things, what does it result in? It results in the we were getting both this chemical shift and chemical and scalar coupling on this axis, right? And then shear transformation, what will this allow us? The F2 axis, right? And following this, this was shear transform. Only on the F2 axis, we will only get this chemical shift. And this is the F1 axis, what we will have? Scalar coupling. So this will help to prevent the overlapping of peaks that we were seeing in NMR, in a 1D NMR. Okay, so that is what it is explained over here. So in a 2D J result NMR spectrum, the F1 dimension displays coupling constants while the F2 or the direct dimension. Why is it called direct dimension? Because it is the detection period. During this time, the signal is detected. So that will display the chemical shift. And this experiment effectively separates the coupling information and the chemical shift information in two different dimensions, allowing for easier interpretation of complex spectra. So what is the so all this purpose of this 2J of this J results NMR spectroscopy? Okay. So what you have to remember that the take home message is the J result spectroscopy. It separates the chemical shift and scalar coupling information. It will separate the chemical shift and scalar coupling information in two dimensions, the F1 dimension and the F2 dimension. So the F1 dimension, in the F1 dimension, what we will get? F1 dimension will have this scalar coupling information. So Fourier transform of the T1 will give you this F1 dimension frequency in the F1 dimension, and this F2 dimension following the shear transformation of the peaks will give us what? Chemical shift information. So what you see, the two informations again are separated in the two different dimensions, one and the F2 dimension. Now we will talk about COSY. Okay, correlation spectroscopy. This is a pulse sequence of the COSY experiment. So here the first pulse. Here first pulse acts as the preparation period, which is followed by the evolution period T1, and the second pulse, this 90-degree X pulse. Again, this second pulse acts as the mixing period. Acts as the mixing period, and following this, there is the detection period. So all these 2D, this is also a type of 2D NMR experiment. So all these 2D NMR experiment will have three parts in it. One is the preparatory time or the preparation time. Then there is evolution period. In the evolution period, you allow the you allow the XY magnetization to interact and uh, and mixing of the spins. Then there is a mixing period. Mixing period and following the mixing period, there is the detection period G2. Okay. Okay. So what I will do, I will add a few more slides. I will try to explain you this COSY experiment, NMR experiment. So, for this, let us consider. So let us consider a two weakly coupled spins. Okay, so we will again take this two weakly coupled spin system. Spin system K and L. Both are having I equal to half. And we will consider that what is JKL. We will consider that JKL is the coupling. It is the coupling constant between the K and L spin system. So what have we considered here? So we have considered that a two weakly coupled spin system KL, and both these spins are having the spin quantum number half, and they're coupled to each other, and the coupling constant between them is JKL. Now the density operator of the spin system at the beginning of the experiment. So if we are at the beginning of the experiment, so in the preparation time, okay, in the preparation time, at the beginning of the experiment, in the preparation time, what will be the density operator? Rho one, what we can write? That rho one equal to I K Z, because the magnetization is in the Z direction initially. So it will be I K Z plus I L Z, right? So you have this K spin and the L spin and magnetization in the Z direction. So the density operator, you can write it as I K Z plus I L Z. Now, what we will do here, this is this one, this I K Z. We will calculate the, so what we will do, we will calculate the evolution of IKZ. Right. So we will only calculate the evolution of IKZ through the pulse sequence. So how is this? This case spin is the K nuclear spin of the effect of this K spin, effect of this magnetization on the K spin, and then the same you can extrapolate it for the L spin also. Okay. So if we calculate the evolution of IKZ through the pulse sequence, then so last session also we had looked at how we operate with this density operators. Okay, at time point T2, and following all this convention, what we can write here is that the density operator rho two at time so rho two means that the density operator at time point T at the time point two in the pulse sequence for this pin K. For this pin K, we can write it as minus I K Y, right? And then this will evolve under the Zeeman Hamiltonian omega k I k z for a time period t1. So this one for this spin k, for this spin k, this will evolve. This evolves. So I'm writing this down so that you can follow well. So under this Zeeman Hamiltonian, I looked into this concept of Hamiltonian. How do you follow the density operator conventions and write this? So in this Zeeman Hamiltonian, this one omega k, okay, omega k I k z, right? Omega set for a period t1, for a period t1, and this will yield what we will. After this spin evolves under this Zeeman Hamiltonian for a period t1, this will yield the density operator rho 3, right? So you get the density operator rho 3, and this rho 3 we can write it as what? So rho 3 is the density operator at time point after time point 3 in the pulse sequence. After time point 3 in the pulse sequence, and then this you can again write it as a minus I ky cos omega k t1 minus I kx, and then what, sine omega k t1. Okay. So the density, so after this K spin, after the K spin evolves under this Zeeman Hamiltonian for the time period T1, for another time period T1, then the density operator at the time point T3, at the time point T3 can be written in this form. And next, if we consider the evolution under the J coupling Hamiltonian, the density operator will be, so under the J coupling Hamiltonian, So under the J coupling Hamiltonian 2 pi JKL I what? IKZ ILZ ILZ. ILZ, then the density operator rho 3. This is rho 3 dash. This density operator rho 3 dash, this will give you a big equation. This will give you what? It will give you I ky cos pi jkl t1 minus 2 ikx ikz. Not ikz, it will be ilz, right? ILZ sine what you can write over here. Sine pi j k l t1, right? Then cos omega k t1, cos omega k t1, okay, and then minus I a x cos pi j k l t1 plus 2 I a y I k y, then I l z I l z sine pi. And again, what you can write? Omega k t1. Okay. So what you are doing here, if you consider the evolution, so if you consider the evolution under the J coupling Hamiltonian, under this J coupling Hamiltonian, 2 pi j k l I k z I l z, right? I 2 pi I k l I k z I l z ILZ, then the density operator, rho 3 dash. This can be written in this form. And then the last pulse transform, these pulse transform, these last pulse transform, this will yield a. So try to understand this. The last pulse transform. So what will do the last pulse? What will it do? It will transform the operators. So it will transform these operators that we were seeing to yield a density operator. It will yield a density operator rho 4. It will yield a density operator rho 4 at time point 4 of the pulse sequence. So rho 4, what is it? Is a density operator at time point t4 of the pulse sequence. So what I'm doing, can you understand? Are you able to understand? So these are the different time points, T1, T2, T3, T4. So what is the density operators at each of these points? Rho. So that will be rho 1, rho 2, rho 3, rho 4. So I'm writing the expressions for these at different time points. At time point T4. Okay. Is it understood now? So at time point T4 of the pulse sequence, then again you can write this one as we had derived for this T3, the row 3, we had derived. Now similarly for that time point T4, the density operator row 4, this you can again write it in this form minus what? I First this electron IKZ cos y j k l t1 plus 2 IKX, right? ILY sin pi j k l t1, right? Cos omega k t1. And then again minus, you put a minus, and then you write it as I kx cos pi j k l t1 minus 2 I kz I lz ly, right? Sin pi j k l t1. Then this will be what? Sin omega k t1 omega k l t1. Okay. Now, since the data is collected soon after this data, this row 4, after this row 4, what is happening? You're immediately after that, you are collecting the data. So one needs what we have to look into that. Then we need to look at only those terms in the density operator. In the density operator, which terms we have to look into? We have to look into those terms which are observable, which are observables. Okay. So the basically what we have to look at the trace of this IXB minus S. This will be not equal to 0. So we have to look for these observable. And thus the observable, this observable part of row 4 is the row 4 observed. So the observable, if we so, after this time T4, after this time T4, we are just detecting the signal. So we in this expression we have to look for only those terms which are the observables. Okay, which are the observables. So if we only look at these terms, then what we can write this equation will get reduced into this form: I kx cos phi j k l t1 minus 2k minus 2k or 2i I kz I ly sin pi j k l t1 sin omega k t1. Okay, this one. Okay, so only this part. This is the observable, right? So this first term, the first term in this equation, if you see this equation for row 4, this first term which represents this X magnetization of the K spin, right? This represents this first term. What does this represent? This represents the X magnetization of the. I'll write this one down separately. It represents the X magnetization of the K spin. X magnetization of the K spin. T2. Right. This first term it indicates what? It represents the X magnetization of K spin that evolves during the time period T2. And it has a frequency that is characteristic of the K spin. Of K spin. So the first term represents X, which the first term which represents X magnetization of the K spin evolves during time period T2 with frequencies characteristic of the K spin. Right. Therefore, this will produce a signal. So, what will this produce? This will produce a signal, a diagonal peak with F1 equal to F2 equal to omega K in the final two-dimensional spectra. In the final two-dimensional spectra, this will give us a diagonal spectra. We will get a diagonal peak. A diagonal peak where F1 and equal to F2 equal to omega or frequency of the spin K, and the second term which represents the Y spin of the. So try to understand this one. So what does the second term indicate? It will indicate the second term which represents Y magnetization, right? What is the second term represents? So the second term obviously it represents a Y magnetization of L spin, right? Of the L spin. Therefore, this term, what will this introduce? This term will produce a cross peak. Okay, so the first term it produces a diagonal peak, and this second term will produce a cross peak. It will produce a cross peak where F1 will be equal to omega K, and if F2 will be equal to omega 1. Okay, both these peaks will have fine structures which contain the coupling information. So both these peaks, these cross peak and the diagonal peak, both these will have fine structures. Uh, and this will have fine structures which contain the coupling information. Okay, so now based on this equation, so the equation that we observe that we obtained here. So based on this equation, what we will do, we will calculate the evolution of the of these terms. We will about how these terms, the first term and the second term that we saw for just now. How does these terms evolved? That has to be considered explicitly. Okay, so we will chemical shift and scalar coupling will be considered explicitly. So we will consider this explicitly, and we will now calculate or we will measure how does these two terms evolve with during the time period T2. Okay, so that first term was what? First term was the diagonal peak. Diagonal peak, and the second term was what? Cross peak. So this diagonal peak. The chemical shift evolution leads to the density operator rho 5D. So What is rho 5D? So this first term. So if we write the density operator for this first term or for the diagonal peak, then this can again be we are what we are trying to understand is which type. How is this first term? What is the evolution of this first term, and then this can be written in this form: ikx cos omega k t2 plus iky, right? IKY. So IKY, when you write, you will get this one sine omega k t2, and then this term FD of Fourier transform of T1. This is not Fourier transform. So here, what does this FD represent? So FD is actually this one that we were getting as in this equation. This one cos this one cos omega cos pi, this cos pi cos omega pi j k, this term we are representing as FD. So this is cos pi j k l t1, right? Sine omega k t1 and omega k t1. So evolution under coupling generates the density operator rho 5d dash. So evolution of this density operator will give us this rho 5d dash. Okay. This will give us this rho 5d dash, and then here you can write it in this form. Or in this form also. IKX cos pi JKL T2 plus 2K 2IKY write it in this form: 2KIY IL Z sin pi JKL T2 cos omega T omega K T2, right? And then KLT2 plus IKY to the cos pi, right? J T2 minus 2IAX I LZ sin pi J L T2 omega K T2 F of D T1 or FD T1. Is it clear now? So, so since we are measuring the Y magnetization, the observable signal here will be given by what? So since we measure the Y magnetization, so since we are measuring the Y magnetization, this the observable signal. So how do we get the observable signal? We had discussed about the trace, finding the trace. So that will be given by what? It will be given by trace of rho 5t dash IKY, right? So what you will get here? Trace of this rho 5d dash IKY. This will give you cos I JKL T2 sine omega A T2. So this will be the observable signal. Okay. Is it clear now? So this you can further solve and ultimately you will get this equation cos pi jkl T2 sine. So if you replace this FD and if you expand it, you will get F T2 cos pi jkl T1 sine omega k T1. Okay. So explicitly, all in all, what you can write here is trace of this one. So 5D dash IKY. Okay. We'll give you 1 by 4. This one sine omega k plus pi j k l. So you solve this and then finally what equation you will get is what I'm writing here. Omega k minus pi j k l T2 sine omega k plus j k l, and then here there will be one T1 and then plus sine omega k minus pi j k l. Okay. So this is what the signal that we are getting, this FID that we are getting. So how will you replace this equation? So this one, this entire expression, this contributes to the detected FID. This is the detected FID that we get. Okay. So the two-dimensional real transformation along the T1 and T2 dimension, it will give us four peaks. Will give us four peaks with the dispersive line shapes at the following frequencies. Okay. So this we perform for this diagonal peak, right? For the diagonal peak, we were doing all these, and then so if we then next if we do the Fourier transform of this, what we will get? We will get four peaks. We will four peaks, and all this will have a dispersive line shape, right? Obviously, they will have from this equation you can make out. We had seen how will this dispersive line shape look like, what will be this expression, and one what will be the case for absorptive line shape. So four peaks with the dispersive line shape and the frequencies, the different frequencies that will get. I have shown this in the next figure. So yeah, so Fourier transform. So this was the free induction decay. You do the Fourier transform, and then here you can see that you are getting four different peaks, and all these these four different peaks have the positive with dispersive line shape, right? So what will be these frequencies? So at the following frequencies: nu k plus jkl by 2, comma vk plus jkl by 2. So positive dispersive frequencies and four different positive dispersive frequencies we will get when we do the Fourier transform of the. So these are the frequencies at which we will get. So vk yeah, nu k plus jkl by 2, and then again here. So these two plus jkl and these two j nu k minus the, so these ones. Okay, okay, and then these ones or these ones. Then again, we can also do this for the second term. For the second term also, what we will do if we do Fourier transform of the second term. So I'll not go into the derivation of this. So if we do the So for the second term, if we do all these calculation, then then what we will get. So this will give us four absorptive peaks. This will give us four absorptive peaks, and if we do the first term, if we do the Fourier transform, and after this calculation, we will get four absorptive peaks. Okay. So now try to solve this question. Okay, and this will be the last question of today's session. The diagonal peak for a two-spin system in a 2D cozy spectra will have the fine structure. So try to solve this question. Just now we derived this and we saw that when we are taking the first term and then doing the Fourier transform, we are getting four frequencies and all these four frequencies have absorptive line shape, positive spectra and absorptive line shape, right? So I've told you the answer now. Yeah, so the correct answer for this question is option B, right? Just now we saw this. All these we are seeing is having positive dispersive line shape. Okay, four weeks with dispersive line shape, and if we do the second term, so these ones. So from here we got two terms, right? This first term and this was the second term. So first term is giving us the diagonal peak, and Fourier transform of the diagonal peak will give us four peaks with absorptive line with dispersive line shape or dispersive line shape, and the second term is giving us the what? It was giving us the cross peak. So if we calculate the scalar coupling, then we get dispersive line shape. Now try to solve this question in a 2D homonuclear cozy experiment. Cross peaks arises due to magnetization transfer mediated by dipolar interaction. Cross peak arises due to magnetization transfer mediated by J coupling interaction. Diagonal peaks arise due to magnetization transfer mediated by dipolar interaction, and diagonal peaks arise due to magnetization transfer mediated by J coupling interactions. So what will be the answer? We saw that the first term was giving us the diagonal peak, second term was giving us the cross peak. And so, yeah, the correct answer is option number B. So the cross peak was arising due to magnetization transfer mediated by J coupling interaction. So, yeah, so try to understand the explanation. Well, in a 2D homonuclear correlation spectroscopy experiment, both diagonal peaks and cross peaks are observed. Now, the diagonal peaks give us what? The diagonal peaks are found along the diagonal of the 2D spectrum. They arise when there is no transfer of magnetization between different spins. Instead, they represent auto correlation, that is, each spin correlates with itself. Right. So in this the diagonal peak, what we were observing that there is no transfer of magnetization, and it representing autocorrelation means each peak is correlated with itself, and the diagonal peaks are related to the chemical shift of the nuclei. Diagonal peaks are related to the chemical shift of the nuclei, and they do not involve any magnetization transfer mechanism like dipolar or J coupling interactions. These are the chemical shifts. Okay, remember this. Chemical shift of the nuclei. And cross peaks. What do the cross peaks in a cozy spectrum are a result of what? It is a result due to transfer of magnetization between two different nuclei through scalar coupling known as J coupling. Okay, cross peaks they arise due to due to scalar coupling, due to transfer of magnetization, and that is transfer of magnetization in between different nuclei will take place through scalar coupling, and this J coupling interaction mediates the transfer of magnetization between coupled spin, creating off diagonals or cross peaks in the spectrum. Okay, so diagonal means this one, and off diagonal or also they are called the cross peaks. So cross peaks arises due to what? It arises due to J coupling or scalar coupling. Scalar coupling taking place between due to transfer of magnetization between two different nuclei. So if we look at each option, so what was the first option? The first option was cross peak arises due to magnetization transferred by dipolar interaction. So this is wrong. It does not arise due to magnetization transfer. It is only arising due to chemical shift, right? Chemical shift arises due to chemical shift. Then the second option, the cross peak arises due to magnetization transfer mediated by J coupling interaction. Okay, so this is correct. This option is correct. Sorry, this is cross peak, right? Not chemical shift. Yeah, so cross peak is not mediated by dipolar interaction. It is rather mediated by J coupling interactions. Magnetization transfer mediated by J coupling interaction. And C option, the diagonal peak arises due to magnetization transfer mediated by dipolar interaction. This is wrong. And the second option is also wrong because in the diagonal peaks, it only arises. There is no transfer of magnetization only in diagonal peak. There is no transfer of matter. There is auto correlation, and they are related to chemical shift of the nuclei. Okay, so it has nothing to do with this magnetization transfer mechanism like dipolar or J coupling. So the option D and option C is incorrect. The correct answer is option B. So I hope this session was proved to be useful. I today what I did is I discussed the concepts related to 2D NMR how what is the general mechanism of 2D NMR experiment, what are the different steps in it, like preparation period, then there is evolution period, mixing period, and then detection period. And then we particularly took one of 2D NMR experiments that is used, that is COSY, correlation spectroscopy. And then we looked at what are the diagonal peaks and cross peaks that is present in a 2D spectra, 2D COSY spectra. Okay, and also we derived these few equations for better understanding of this COSY experiment, and then we solve these questions. We talked about the J-result spectroscopy, how we differentiate or we separate the two parameters, this chemical shift and the scalar coupling, and all these were discussed. So I hope this session was useful. And if you have any further doubts, we can take it up in the next class. So till then, you go through the lectures and see you in the next session then. Okay. Thank you.